about basic models. So this is the outline of the presentation. We'll mainly talk about strategic games and normal representation. We'll go through extensive games and game trees. We'll talk about reduced and sequential representations, and finally, we summarize. Okay, so what are strategic games? So in fact, the most simple way to represent a game is to use the strategic form. And we need to specify the set of players, of course, as in any game. And we need also to detail the set of options like strategies available to each player. We need to describe the way the players pay off, and we mean by that utilities depend on the options that they choose. And the game model should be as close as possible to the situation, of course, we are trying to analyze. What is a strategy profile? A strategy profile here is a combination of strategies that the players might choose. From a mathematical point of view, this is the notation one can introduce. So formally, what is a strategy form game? A strategy form game is any gamma game of the form where it is a set of four players. For every player in capital N, we have a set of strategies, and we do have for every player in N, we have a kind of utility functions or utility mapping. Of course, the set of players N is an empty set representing the set of game players. Si is also considered as a non-empty set representing the set of pure strategies available to each player, I. And we'll have the cross product of all the set of all possible strategy profiles, which we may call S. For all J in N, this is the Cartesian product or the cross product of all the possible strategy profiles. So UI here is the utility of player I, and could be defined as a function from S into the set of real numbers R. And we also assume that each player I expresses his decision using a vector xi, which represents a probability distribution over his set of strategies. So what are the game rules? Every game has its own rules. So when we study strategic form game, we assume that all players formulate their strategic choices simultaneously. So this is basically a one-shot game. And there is also no time element here in the analysis of strategic form games. So obviously, eliminating the timing and the time elements from our analysis can have substantial consequences on our game model. Strategic form games are generally assumed to be finite, and in terms of number of players. So N is a finite set. And the game rules should be carefully represented in our model. So what about a small example? So in this small example, which we call the penalty shot games, we have a player one, which has to take a soccer penalty, football penalty shot to decide the game. So she can shoot left, middle, or right. And player two, who's the goalie, he can dive to the left, middle, or right. And the actions here are chosen simultaneously. So payoffs, which here represent the probability intent of winning, are as follows. So here for player one, who's the shooter, you have capital L, capital M, capital R, which represent the shooting strategy. And for player two, who's the goalie, you have small l, small m, and small r, which represent the diving strategy. So for instance, if player one shoots on the left, he has 40% probability to make the shot, 60% to miss it. If he chooses, if the player two, of course, jumps to the left, but if he chooses to the left and player two stays in the middle or dives in the middle, he has 70% probability to make the shot, 30% to miss it. Okay, so this summarizes the payoffs of the game. So let's go through some of the questions you have for this game. So you may see that for the first question, for each player, the question is any strategy dominated by any other pure strategy. So here, in terms of pure strategies, none of these strategies, in fact, is dominated by another pure strategy. So for instance, for the shooter or player one, if I'm expecting the goalie to stay in the middle, I will have what? I will have to prefer what? So between 4, 6, and 9, you see shooting in to the left is dominated. So if I'm expecting the goalie to stay to jump to the left, to dive to the left, capital L is dominated. However, in the case I'm expecting him to be in the middle, capital M is dominated. And if I'm expecting him to dive to the right, capital R is dominated. So none of the pure strategies of the shooter is dominated by any of his other pure strategies. However, one things we worked on is that one can notice that possibly this strategy of shooting to the left or to the right or in the middle could be dominated by a combination of the two remaining pure strategies. For example, the strategy here, which is shooting in the middle, okay, would be dominated by half of strategy capital R and half of strategy capital L. And you can see, so in this case, all what is provided by capital L is always dominated by half of capital R, half of capital M. L. And here we talked about the possibility that a pure strategy is strictly dominated by a combination of the other pure strategy. Okay? Here in the first case, we'll get, if I'm expecting the goalie to dive to the left, I'll get 4 plus 9 divided by 2, which is 13/2, which strictly dominates 6. And the second case, if I'm shooting in the middle, I'll get half of 7 plus half of 7, which is 7, which strictly dominates 3. And the last case, if I'm expecting the goalie to dive to the right, I'll also get 13/2, which strictly dominates 6. Okay, so the strategy capital M, which is shooting in the middle here, is always strictly dominated by a combination of shooting to the left and shooting to the right. Okay, so now the second question was, for what beliefs of player 1 strategy is M a best response for player 2? M is best response for player 2. When do we have M as a best response for player 2? I mean, which maximizes the outcome for player. Yeah, for if I believe, of course, that player 1 is shooting in the middle, for sure, I would dive to the middle. Okay. So this is the third question. For what beliefs of player 2's strategy is capital M the best response for player 1? Okay, for sure. In that case, if I want to maximize my income, shooting in the middle has the highest probability of return. Case I'm expecting the other player to the goalie to dive to the left or to the right. Okay. So we can see that in none of these scenarios, capital M is the best response to small m. Okay. So the third and last question was that supposing that player 2 puts himself in player 1's shoes and assumes that player 1, whatever his belief, will always choose best response to that belief, should player 2 ever play small m? Well, here that builds on what? That builds on the fact that capital M strategy should be anticipated to be eliminated as a strictly dominated strategy by player 1. So in that case, well, my player 2, which is the goalie, will never play small m, okay? Because he will have to remove this strategy. Okay. So just to go again with normal representation. So the normal representation of our penalty shot game, in fact, described how at the beginning of the game, the expected utility payoffs to each player would depend on their strategic plans. And it represents, in fact, the decision theoretic situation that confronts the players as they plan their strategy. So it could be used also to represent other forms of games, such as extensive form games in terms of reduction or reduced matrices. So in that case, it uses matrices or tables where rows and columns correspond to the strategies available to the players and the entries correspond to their respective payoffs. Now, the second part of the presentation about what we call the extensive games. So, in fact, together with the normal form, the extensive form is one of the most important forms used to model a game. And the extensive form is the most, in fact, the most richly structured way to describe game situations. So the strategic form is generally considered to be derived from the extensive form. And the extensive form models, in fact, a situation where decisions are not taken simultaneously by all players. So the extensive form models a dynamic confrontation where players can have different strategy sets at each of the game stages. And the extensive form, again, can be represented using what we call a game tree, a normal representation, or also a sequential representation. So let's start first by the game tree representation. What is a game tree? Game trees, in fact, offer the most complete description of an extensive form game. And in graph theory, a tree is generally defined as any graph without cycles. So as a graph, a tree contains a set of nodes and a set of arcs. And for extensive form games, the game states are represented using the tree nodes. So the root node, for instance, indicates the beginning of the game, and each leaf or terminal node indicates the end of the game. And at the end of the game, each player would receive a payoff. So the non-terminal nodes are considered as decision trees or decision nodes for our players. And the players' moves are attributed or to the outgoing branches or arcs from these decision nodes. So from a game tree language point of view, each possible sequence of moves is represented by what we call a path of play. So by a path from the root to one of the terminal nodes. And Kuhn in 1953 introduces the partition of the decision nodes into information sets. And considering all nodes in an information set as nodes belonging to the same players and having the same moves, a deciding player knows only the information set, but not the particular node he's at. And here we talk exclusively about how important is it to define what we call the information set for the nodes of our game tree. In n-person extensive games, each non-terminal node has what we call a player label in the set capital N of players, and a zero node, a zero label node represents a chains node. And each node controlled by a player has a second label indicating the information set. So a player may have a different number of information sets than the number of the decision nodes which belong to him, or the number of opportunities or possibilities of play in the game tree. So let us add more and more about game trees. So it's generally assumed also that players have perfect recall in an extensive game. So each deciding player remembers all the information he knew early in the game, including his past moves. And any pair of nodes that have the same player and an information set label should have the same strategy sets. Okay, this is quite important. Any pair of nodes that have the same player and information set labels should have the same strategy sets. So a subgame is defined where? It's defined as a subtree, including all information set that contain a node of the subtree. Okay, we'll go back to this in the fourth set of slides we cover in this course in details when we will try to find find equilibria for extensive form games. So this distinction has to be made here between games with perfect information and games with imperfect information. So in a perfect information game, each information set is a singleton, and each node is a root of a subgame. Okay, because at any decision node, we know exactly what happened before. And no two nodes here will have the same information set. Let's see this small example. So in this small example from Van Stengel Eliab paper, which appeared in 2002, we have a game tree, and the root node belongs to player one, and he has the possibility to play either capital R and capital L. If he plays capital R, the game ends, and player one gets 3 as the final payoff, player two gets 4. If player one decides to play capital L, then player two has the opportunity to play small l or small r, which leads to a situation where player one has the opportunity to reply. And he or she would possibly move S or T, which will end the game by distributing these payoffs. So player one, to summarize, plays once or twice, where player two may not play or plays at most one time. Okay, so player one has at most has 2 alternatives in his first strategy or his first information set. and has 2 strategies in his second information set. Okay, so if player 1 chooses to play at his first move, player 2 will have 2 alternatives, small l and small r. And if player 2 decides to play small l or small r, player 1 will have 2 other alternatives, capital S or capital T. Okay, so we covered this part about the details of the game. So let's talk first of all about the reduced representation, how to convert this extensive form game to kind of from normal representation. So it is possible to use a reduced normal representation. And the pure strategies of player 1 here would be the following combination, either LS, LT, or RS and RT. So there are 4 possible combinations. And of course, it is even possible to replace RS and RT by the single reduced strategy, which is capital R, because whatever happens if player 1 plays R, there is no way he can play S or T. And that represents the top row of the subsequent normal form payoff matrix you see here. Okay, so if player 1 plays capital R, whatever happens, he ends up with 3 as the final payoff. And player 2 basically has nothing to do. Okay, and if he plays LS or LT, these are the corresponding payoffs inherited from the terminal nodes of the game tree. Okay, so some critics about this reduced representation. The reduced normal representation is the most simple representation of an excessive game. However, the timing element, as you've seen in these matrices, is lost. And the link between strategies available at the same information set is lost. So this might limit the solution space of our game, and we have to think about a method which limits the information loss. One of the remedies to this is to use what we call the sequential representation. And it's possible to use sequential representation as first proposed by Weinstein 2002. And there is a unique path, in fact, in the game tree which link the root node to any node of the game tree. So for a given node, this path, in fact, would define a sequence of moves for each player. And the move sequences for player for player 1 would be RL, LS, and LT. And you can see that there is a link between LS, LT, and capital L. While the move sequence for player 2 is much more simple, it's just small r and small l. And since some players like player 2 may not be able to play, we may also add an empty sequence to each set of move sequences, which would give us the following sequences of moves for player 1, like the empty sequence R and L, and you have LS and LT that are completely linked to the partial sequence, which is L. While for player 2, we have these sequences, empty sequence, small r and small l. Okay, and you see how the payoffs now are represented. Okay, so to be able to model this within a linear program, or to be able to link small l to small r, or to the initial notation of probability, we also defined what we call the sequence matrices, E1 and E2. And basically, we said that this one here represents the initial notation of probability, which is the 1 unit or 100% notation probability we enter the game with for player 1. And this 100% will be split between capital R and capital L. So the probability MT would be equal to XR plus XL. And the probability attributed to XL would be split into XLS and XLT. Okay. In fact, the beauty of these sequencing matrices is that they allow us to really encrypt this link between these sequences of moves. In fact, okay. So to summarize, the form chosen to represent a game should be as close as possible to the real problem, and the normal form is the most simple representation of a game, and the extensive form is in fact the most complete representation of a game. The reduced normal representation of an extensive form game may help to solve but yield information loss, while the sequence representation carries much more information. And here, if you recall, we developed on the multi-hall problem, the case where we have this show where there are 3 doors, and behind 2 of the doors there is a goat, behind 1 of the doors there is a car, and the player has to pick 1 door in first round, and the show host would open one of the doors remaining with the goat behind and ask the player to move or not. And we've shown during the class that, well, moving or not in the second round is kind of dominated or would always bring a lower result than not move. Okay, we've shown that. Okay, thank you very much for following, and we'll proceed again with another lecture video. Thank you.